want to see the properties of the covalent bond. Okay, the dative bond is the same as the ordinary covalent bond. They are the same. Okay, except just in the fact of how it is formed. Okay, other properties like the strength, the length of the bond, okay, they are the same as the ordinary covalent bond. Okay, so we want to continue with the properties of the covalent bond. Okay, there are several properties that we'll discuss. Okay, let's start with the first property, which is the bond order. Okay, this is the first property. Bond order. There are three bond orders. Okay, the first one, if we have a single bond, okay, if we have a bond that is made, okay, and it is a single bond, example in the HCl or HF, okay, they are forming a single bond with each other. Okay, it is when they are sharing a pair of electron. When they are sharing a pair of electron, then they form a single bond. That is represented by a single dash. Okay, this one. Okay, that single bond represented by the single dash between that two atoms. And when we have a single bond, we have to know that the bond is a sigma bond. Okay, when we have a single bond, the bond is actually sigma bond. What is sigma bond? We'll discuss after this. Okay, remember it first. Okay, when we have a single bond, then the bond is actually sigma type. Okay, and come back to the properties. It is about the bond order. When we have a single bond, okay, the bond order is actually first order. Okay, single bond, it is first order. Okay, double bond. If you have a double bond, it means that the two atoms share two pairs of electron. Okay, the two atoms share two pairs of electron that is represented by this double dash between that two atoms. Okay, example in oxygen, if we draw the structure of oxygen, O will form two bonds with the second oxygen. Okay, so they are sharing two pairs of electron. Then we said that the bond order in oxygen molecule, the bond order in oxygen molecule is second order. So double bond, it is second order, simple. Okay, and when we have a double bond, we know that there are two bonds made between them, right? Okay, the first bond will be a sigma bond, and second bond is a pi bond. Okay, we'll discuss after this what is sigma and pi. Don't worry. Okay, let's look at to the third bond order. Okay, when we have a triple bond, example in nitrogen. Okay, nitrogen is actually formed when the two atoms of nitrogen are sharing three pairs of electron. Okay, they are sharing three pairs of electron between them. Okay, then they are forming triple bond represented by this triple dash. Okay, and the bond order will be third order. Okay, the bond order in nitrogen is third order. And when we have this triple bond, okay, the first bond is a sigma bond. Okay, and then another two, they are pi bond. Okay, the first bond is always sigma. Okay, then the subsequent bonds are pi. So if we have double bond, the first one will be sigma, second is pi. If we have triple, first sigma, the second and the third are pi bond. Okay, and the bond order when we have triple bond is third order. Okay, the second property is finished with the first property, which is bond order. Now we move to the bond energy. Okay, so bond energy is defined as the amount of energy that is required to break a covalent bond. Okay, so I have a covalent bond in H2. Okay, how much energy that is needed to break this bond? Okay, the energy that is needed to break this bond, okay, per mole is what we call as the bond energy. Of course, that if we have a weaker bond, okay, bond that is weak. A weaker bond means that the bond is unstable. It is less stable. So when the bond is less stable, it will make the molecule is also less stable, and that molecule will be more reactive, easier to react. Okay, it is easier to react. It is because if we want the reaction to occur, okay, then the former bond need to be break and the new bond need to be formed. Okay, so if it is easier to happen, okay, former bond it is easier to be break and new bond is easy to be formed. So we said that they are reactive. They are easy to react. Okay, so this is happen when we have a weaker bond. Okay, when we have a weaker bond means that it is easier to break than we compare with the stronger bond. Okay, so if we have a stronger bond, okay, means that the molecule is more stable and it is harder to react. It is less reactive. Okay, so of course that the relationship is, okay, the greater the bond energy, okay, leads or it is actually indicate that the bond is stronger. Okay, the greater the bond energy, the stronger the bond. Okay, the stronger the bond, the more energy need to be provided to break it. Okay. So what is the relationship between the bond energy and electronegativity? Remember, we have discussed electronegativity is the ability of the atom to attract the electron. Okay. So the ability of the atom to attract electrons. So we know that within the periodic table, okay, the electronegativity will increase across the period towards the fluorine and increase going up the group. Okay. It is increasing to the more smaller size of the atom. Okay. Then how to relate it to the bond energy? So when the electronegativity differences beza in the electronegativity form, okay, between the two atoms, okay, it will make the bond strength or bond energy increase. Okay, bond strength, bond energy, they are the same. Okay, how to determine the electronegativity differences? Okay, okay, let's look at to the textbook, look at to the data on the EN value last time. Can someone search the page of the electronegativity value? It is in a figure.
Madam, is it page 390?
390 ke
Yes.
319?
I'm not sure.
Sekejap, let me check. Yes, correct. 390. Okay. So that are the figure 9.2. Okay, the electronegativity value of several of the elements in the periodic table. Now we want to relate between the bond energy and the electronegativity differences. Okay, if let's say we have a bond that is made between the HF, HCl, and HBr. Okay, look at to the electronegativity value of the hydrogen. What is the EN value of hydrogen?
2.1.
It is
2.1.
2.1, correct. What is the electronegativity value of fluorine?
4.0.
4.
It is 4.0. Chlorine?
3.
Betul, 3.0.
Betul.
Yes, and then bromine?
2.8.
2.8, right? Yes. So when we calculate delta En, remember delta? Delta is the changes, the difference in the electronegativity. So the delta En for the first one, HF, will be 4 minus 2.1, which is equal to 1.9. Okay, the delta En, beza in the electronegativity value between chlorine and hydrogen will be 3 minus 2.1, which is equal to 0.9. And then for the H and Br, their delta En is 2.8 minus 2.1. So dia punya delta En is only 0.7. Okay. So the greater the difference in the electronegativity, okay, the greater the difference in the electronegativity between the two bonded atom will make the bond between them become stronger. Okay. That can be observed by this value. Okay, the delta En that is highest is in HF and then followed by HCl and then followed by the HBr. Okay, so this bond is the strongest one and then this bond and the weakest one is this bond. Okay, so if the strength is on that trend, okay, on that arrangement, then it is related to the energy as well. The stronger the bond, the more energy is needed to break it so that the bond energy will be higher. Okay, one of the factors that determine the strength of the bond is this delta En, the difference in electronegativity. Okay, the bond energy or the bond strength is also related to the bond order and also the bond length, panjang bond tu. Okay, we will get to the bond length first. But basically, okay, from this, the relationship between the bond energy and the delta En is the greater the delta En, the higher the bond energy. So they are directly proportional. Okay. Example is Hi decompose easily. Okay, it is easier to decompose Hi. Decompose means that we break the bond in it. Hi is easier to decompose means that we break the bond there. Okay, and then we compare it with the HCl. Okay, so it said that Hi is easier to be break. Okay, when it is heated to the rate heat, but HCl does not. Okay, why? This is because the bond in Hi is weaker than HCl. Okay, look at to the bond energy value. Hi has a lower bond energy value than HCl. So because of this bond that is weak, it just require less energy or minimum energy to break it. Okay, so this is what I said just now. Okay, the bond order also affect the bond energy, the bond strength. So if we have a triple bond, it is stronger than double bond and double bond is stronger than single bond. Okay, when we have triple stronger than double, it is stronger than single. Okay, then example is given here, okay, in which the nitrogen molecule is unreactive. What is the meaning of unreactive? It is hard to react. Okay, react means that they are able to break the former bond and form new bond. Okay, then why the nitrogen become unreactive? Because of the bond energy is 944 kilojoule per mole. Means that to break a bond in nitrogen, in which we know that nitrogen has triple bond. Okay, so to break these three bonds between the two nitrogen atoms, it requires 944 kilojoule energy. Okay, if we break one mole lah. Okay, the energy is not just to break one bond in nitrogen. It is to break 6.02 exponent 23. Remember, this is for one mole. Okay, that is why the unit is kilojoule per mole. Okay. But basically, when we have a triple bond, it is stronger. That is why it become unreactive. Okay, and require more energy to break it. Okay, the third properties is the bond length. Okay, so the bond length is defined as the distance between the nucleus of the two atoms in the bond. Okay, the nucleus of the two bonded atom. This is the first bonded atom. This is the second bonded atom. Okay, the nucleus of the first atom to the second atom. Okay, the distance of them is what we call as the bond length. Okay, now look at to the bond that is made between hydrogen. Okay, so the bond length will be start from this point to this point. Okay, so we connect them. So that is the bond length, which is 74 pm. Okay, as compared to the bond that is made between H and I. Okay, this is the first nucleus. Okay, this is the second nucleus. Okay, obviously from this figure, which one that have a longer bond? Shahira. H2 or Hi that have a longer bond?
HI.
Why Hi have a longer bond?
I think
From your
because
observation.
the I radius is bigger.
Yes, because of the size of iodine that is bigger. Okay, we are having the same H atom. This is H atom. This is also H atom. The difference between these two molecules is at the second atom bonded, right? This is hydrogen and this is iodine. Okay, so obviously that this bond is longer because of the size of the atom that is bigger. This iodine is bigger than this H. So the bigger the size will make the bond become longer. Okay, so the factor that determine the bond length is actually the size. Okay, it is not just size. Okay, the bond order or the number of bond made also will determine the length. Okay, in which the multiple bond, okay, will be shorter than the single bond. It means that single bond, if you have a single bond, it will be longer than double bond. It is longer than triple. Triple bond is the shortest one. Single bond is the longest one. Okay. So as the example given here, okay, for the carbon and nitrogen, triple bond are shorter than double bond, in which in terms of the shorter than a single bond. Okay, look at to the table. Look at to the carbon. Okay, carbon, single carbon. Carbon, single carbon here. This is the bond length 154. Okay, and then carbon, double carbon. Okay, the length is 133 and carbon, triple carbon. Okay, the bonds is made between the same two atoms, means that the size of the carbons are the same. Okay, it is not the size factor that determine the length because the atoms are the same. The bond made between carbon and carbon for all these three. Okay, that we are referring. Okay, but when you look at to the bond length, okay, we observe that C single C is the longest one, 154. C double 133 and C triple 120. Okay. And then that is the bond order factor or the number of bonds made between the two at the same two atoms. Okay, now let's look at to the size factor. Okay, if we look at to the size factor, we are comparing, okay, the second set, we are comparing CH, CO, and CC. CH, CO, and CC. Okay, we need to look at to the size of the hydrogen, size of oxygen, and size of the carbon that will differentiate their length, their bond length. Okay, now hydrogen, it is a period 1 element. It is the first element. Of course that it is the smallest one. It has only one electron. So the size of hydrogen is the smallest. Okay, then oxygen and carbon. Okay, look at in your periodic table the position of the carbon and oxygen. Okay, they come from the same period in which oxygen is group 16 and carbon group 14. Okay, we know that across the period, the size decreases, right? So that the oxygen is smaller than carbon. Okay, oxygen size is smaller than carbon. So if we arrange the size trend from the smallest to the biggest one, the smallest is hydrogen. It is smaller than oxygen. It is smaller than carbon. Okay, that is why the bond length, okay, will be shortest between carbon and hydrogen. Okay, it is shorter than carbon and oxygen, and it is shorter than carbon with carbon. Okay, carbon-carbon is the longest one. Okay, that is proved by this value 154. This is the longest one, C single C. And then C single O is 143. And C single H is 107. Okay, remember the factors that affect the bond length. Okay, bond order. Okay, the higher the bond order, the shorter the length. Okay, and also second is the size of the bonded atom. The bigger the size of the bonded atom, then the length will be longer as well. Okay, the bond will be longer. Okay, example that is given here, C single C, C single Br, and C single I. Okay, look at to the position of the chlorine, bromine, and iodine in the periodic table. We don't need to look at to the carbon because they are bonded to the same carbon atom. Okay, the difference is at the chlorine size, bromine size, and iodine. They also form the same order, which is single bond, single bond, single bond. So the factor that will determine the length is due to the size. Okay, so from the periodic table, we know that the smallest one is chlorine because chlorine is in the period 3. Okay, so chlorine is smaller than bromine, come from period 4. Bromine is smaller than iodine. Okay, of course that the bond length will be highest at the Ci. Okay, because iodine is the biggest, so 0.214, Br shorter 0.193, and CCl 0.171. Okay, shortest. Then look at to the bond energy value. Okay, look at to the bond energy. The shortest one will have a highest bond energy. The longest one will have a lowest bond energy. It means that the bond length is inversely proportional to the bond energy. Okay, the shorter bond will be stronger, will be harder to break. Okay, as compared to the longer one. Longer one will be weaker and easier to break. Okay, so that we can make conclusion. Okay, from that, okay, the shorter the bond length, the stronger the bond. Okay, shorter length, bond will be stronger. And then we also can look at it in terms of the electronegativity differences. When the delta En increase, bond length will decrease. Bond length will decrease. Bond length decrease, bond strength will increase. Okay, because we know that when we discussed bond energy just now, bond energy is directly proportional to delta En, electronegativity differences. Okay, and we know that bond energy here is inversely proportional to bond length. So that we can add another one, it is 1 over BL. Okay, bond energy is inversely proportional to the bond length. Okay, and then the third one, the number of the covalent bond between the two atoms increases, distance will decrease. Okay, the more covalent bond made means that the triple bond is shorter than double, double is shorter than single. Okay, it means that the bond energy is directly proportional to the bond order, and it is also inversely proportional to the bond length, bond energy. Okay, the higher the energy that is needed to break the bond means that the bond is shorter. The less energy that is needed to break the bond means that the bond length is longer. Okay. Higher energy, shorter length. Low energy, longer bond. Okay, we have this table in the textbook. It lists all the bond length and bond energy, okay, that we have between the two atoms. Okay, we have so many examples here. Okay, that you can check. Okay, if you are interested in. Okay, if we compare between OH, OP, OO, OH, OP, and O, oxygen. Okay, so actually we have to compare between HP dengan oxygen. Okay, so if we want to compare it, look at to the periodic table. Hydrogen is the first element. Of course that it is the smallest one, right? And then phosphorus come from period 3. Oxygen period 2. Of course that oxygen is smaller than phosphorus. Period 3, period 2. So if we look at to the size punya trend, hydrogen is smaller than oxygen. Oxygen is smaller than phosphorus. So that the bond length will be OH is shorter than OO. It is shorter than OP. Okay, then look at to the value. See, 96, 148, and then 160 is the longest one. Okay, and the bond energy will be opposite trend. Okay, the bond energy will be opposite trend. We know that the shorter the bond, the stronger the bond. So that generally, okay, we make a conclusion. Okay, the bond energy, okay, which is the same as the bond strength, okay, is directly proportional to the bond order. Means that the higher the order, the stronger the bond. Okay, it is also directly proportional to the delta E and the difference in electronegativity. Okay, the higher the difference in their electronegativity, the stronger the bond. Okay, the stronger the bond, the more energy that is needed. Okay, and then it is inversely proportional to the bond length. Okay, so these are the formula that you have to remember, the relationship between them. Okay, another example is given in a table 9.3 as what we have discussed. Okay, between a single, double, triple, bond order will be first, second, third order. Okay, look at to the length, single longest, triple shortest. Look at to the bond energy, single have a lowest bond energy, and then triple have a highest bond energy. Okay, and then the last property of the covalent bond is the bond polarity. Okay, the last one is the bond polarity, only up to this point, bond polarity. Okay, the dipole moment and polarity of the molecule we'll discuss after this. Okay, but this is the last property of the covalent bond. Okay, what is the polar bond? Okay, polar bond is defined as the bond that is made between the two atoms that have different in their electronegativity. Okay, if we have a bond that is made between the two atoms, A form a bond with B, and then A has different En value as what we have calculated just now. Okay, when the En, the electronegativity value of A is different between the electronegativity value of B, it will mix the distribution of the density of the bonding electron pairs is asymmetrical. Okay, when their electronegativity are different, okay, the electron density Okay, between these two atoms will become asymmetrical, not symmetrical, not balanced. Okay, electron density will not balance. And if let's say B is more electronegative than A. Okay, so if B is more electronegative than A, so that the electron density will be higher at the B region. Okay, so more electron will be at the B region, which low electron density at the A region. It will makes the bond become asymmetrical. Okay, because of the distribution of the electron that is not balanced, that is not symmetrical. Okay, so due to this asymmetrical distribution of the electron density, then we said that the bond is a polar bond. As compared to if the bond made between the two atoms that have the same electronegativity. Okay, for example, if we have a bond between fluorine just now. Yes, we know that fluorine is the most electronegative atom. But since that these two atoms has the same ability to attract the electron, so it will make the electron density between them become balanced, asymmetrical. It is symmetrical, bukan asy. Okay. The electron density becomes symmetrical or balanced or the same distribution of the electron. Okay, then the bond is non-polar bond. It is non-polar. So basically the polar bond is actually arise when the two atoms that form bond with each other have different electronegativity value. So the electron will be higher at the one that is more electronegative. Okay, and it will make the density of the electron become imbalanced, become asymmetrical. Okay, that is the difference between polar and non-polar bond. Okay, so these are the patterns of the electronegativity towards fluorine. Okay, and the direction of the polarity of the bond can be symbolized by this vector quantity. Okay, the cross end of the arrow, okay, the cross end here is at the positive end while the arrowhead is at the negative end. Sorry, this cross one at the one that is more electropositive. Okay, the head is at the one that is more electronegative. Example here, hydrogen and chlorine. Chlorine is more electronegative than hydrogen, so that the bond become polar. Okay, because the electron will be higher at the chlorine region. Chlorine is more electronegative. So we have to show the polarity of the bond. Okay, we say that it is polar, then we have to show the polarity of the bond. Which side that will have a higher electron density by using this vector quantity. Let me rewrite. Okay, so this bond is polar, so this is how we show it. Okay, the polarity is moving towards chlorine. Chlorine is more electronegative than hydrogen. Okay. Mm, if the covalent bond is made between atom of the same element, then it is non-polar. Okay, example is given fluorine, oxygen, ozone, okay, nitrogen triple bond. Okay, the bond is made between the same atom, so that the bonding electron will be shared equally. Okay, this is a symmetrical distribution. Okay, the bonding electron are shared equally. Okay, it will make all bonds become non-polar. Okay, as compared to if the covalent bond made between different atoms. Okay, so the bonding electron will be closer to the one that is more electronegative. Okay, so that the bond is polar. It's always polar if we talk about the bond. However, the molecule as a whole, okay, the molecule as a whole can be polar or sometimes non-polar, depends on the shape. Okay, we'll discuss on the shape first before we discuss on the polarity of the molecule. Okay, today we just discuss the polarity of the bond only. Okay, the bond polarity. Okay, so bond will have different polarity. Okay, example, if we have a bond between, example this now is a HF. Okay, we compare it with the HCl. We compare it with the HBr, right? Okay, we know that the electron distribution here, they are all not symmetrical. They are all asymmetrical because of the difference in the electronegativity of the two atoms. Okay, they are not the same atom, so that the electron distribution will not symmetrical. Okay, they are not balanced, so they will move towards fluorine for the first one. Okay, so we show the polarity by using this. And then hydrogen chlorine, we know that chlorine is more electronegative, so the bond also polar towards chlorine. And then HBr, Br is more electronegative. This bond also polar towards bromine. Okay, so we know that they are all non-polar, but we have to know which one that is the most polar one. Okay, which one that is least polar bond. Okay, so the polarity of the bond is actually depends on the delta En value. Okay, the difference in electronegativity that we have calculated just now. Okay, we know that hydrogen is 2.1, fluorine is 4. We know that hydrogen is 2.1, chlorine is 3.0. Hydrogen is 2.1, bromine is 2.9. Am I right? 2.8. So that the delta En for the first one will be 1.9. Here is 0.9. Here is 0.7. Okay, so the greater the delta En value, then the bond become more polar. Okay, the more polar the bond means that the electron distribution becomes so imbalanced as compared to the one that is least polar. It is imbalanced, but not as imbalanced as the one that is more polar than it. Okay, so the bond polarity range, okay, the bond polarity arrangement, okay, or trend, okay, least polar is HBr and then HCl, and the most polar one is the HF. Okay, so if we refresh back the formula last time, okay, the bond energy, we want to recap all. The bond energy is directly proportional to the bond order. Okay, bond energy also directly proportional to the delta En. And it is also, of course, directly proportional to the bond polarity. Okay, now we start to have a bond polarity. Okay, bond energy, bond order, delta En, bond polarity. What else? It is inversely proportional to the bond length.